Hello, everyone. My name is Alessandro Ricottone, and I am a research scientist for the Lisk project. In these 2 days, my fellow colleagues gave you a lot of details about the upcoming Lisk interoperability solution. So now, in this talk, I want to put it all together and put the final piece of the puzzle in and talk about interoperability from the point of view of the Lisk SDK. For those of you that don't know it, the Lisk SDK is a tool that developers can use to develop and deploy a blockchain application. By now, the SDK is a very mature product that reached version 5, and we will hear many more details in the next deep dive session. I want to talk here about what is going to come in the next iteration of the SDK, the one that will bring interoperability in. In particular, with the next iteration, developers will be able to create and deploy an interoperable blockchain application. So here is an overlook of my presentation. I will first present the updated modules architecture, and then focus in on the interoperability module, the module that will come out of the box with the Lisk SDK, and will provide all the functionalities needed for interoperability. And finally, the research team prepared a small example of an interoperable blockchain application. This will be kind of the point where I put together the ideas that I present and explain how you could, in practice, develop an interoperable blockchain application. But let's start with the updated modules architecture. So modules are at the core of a Lisk blockchain. Modules are responsible, in particular, for adding the protocol logic to the blockchain. To do so, they define hooks that inject this protocol logic during the block lifecycle. They define reducers, which are exposed interface to other modules. They define the assets for custom transactions, where all the custom logic defined by the developer happens. They define action and events that are used to provide information to external systems and plugins. And finally, these last 2 points, which are the novelties that are coming with the new SDK, each module will define a storage interface and the assets and processing for cross-chain messages. Let's start with the state model. Each module, as I mentioned, will define a store, which is part of the blockchain state. So in this picture here, you've seen this already today. I show the state tree. Each colored box at the bottom corresponds to a different module registered in the blockchain application. On the left, we have the default modules that come already packaged in the Lisk SDK. These modules are, for example, the token standards that Maxime presented, the depots module, or, for instance, the interoperability module. On the right instead, we have the custom modules. Those are the modules that will be developed by the developers of the blockchain application. And at the end, the whole state of the chain is authenticated by the state root. As Andreas presented, this state root is used in certificates then to validate cross-chain messages. If we zoom in into one of these module store, each leaf of this subtree corresponds to an entry in the database. And the entry is identified by the module ID, telling us in which subtree we have to look, the storage prefix, and the storage key. The storage prefix here plays a similar role to the module ID. We use it to separate subtrees. It's basically to separate different buckets within the same database. And the key identified each single entries. Modules also define schemas that are used for data serialization, and the value of the leaf will then be the serialized data structure according to the schema. Hooks, I'm going to give you just a refresher here. Again, many more details upcoming in the next session. Hooks are used to add the logic to the block lifecycle. So when a new block is processed, we first verify some basic properties of the block, and then the before block apply hook is called. And then for each transaction in the block, we go through these 3 steps of before transaction apply, and after transaction apply. After all the transactions have been processed like this, finally, we have the after block apply hook, and if everything went well, the processing has been successful, and all state changes have been saved. So modules can inject protocol logic during each one of these steps. Reducers, as I mentioned before, and as Maxime discussed in his presentation, are exposed interfaces that other modules can call. Basically, the idea here is that each module has agency over its own store. So for instance, the token module should be the only one that is allowed to modify the balances in the state tree. But of course, other modules can trigger this logic by calling the reducer. So let's look at an example of this. The vote transaction in the delegated proof of stake module first creates a vote object in the depot store, but then calls the token lock reducer to lock tokens in the token store. And finally, increases the delegate votes, again, in the depot store. OK, custom transactions. Well, this is where all the magic happens. This is what defines and where the custom logic is processed using the transaction asset. A module defines the schema for the asset structure and defines two functions. The first one, validate to validate the asset, and the second one, to apply the asset and run the custom logic. But with interoperability comes a new data structure that we're introducing, cross-chain messages. And in the same sense in which transaction trigger a state transition in a blockchain, cross-chain messages are used to trigger a state transition in a different blockchain. Modules will define the custom logic around cross-chain messages. In particular, the custom logic around sending a cross-chain message. So cross-chain transaction will be able to spawn one or multiple cross-chain messages. And the logic around receiving cross-chain messages. Because when a cross-chain message arrives, is included into a chain as part of a cross-chain update, it is processed and, as I mentioned, triggers a state transition. So they're very similar to transaction. In particular, they have an asset where the custom logic is included, but they also specify some properties, other properties, and in particular, the sending chain ID and receiving chain ID, because as I mentioned, these are state transitions that happen in a different chain from the sending chain. OK. Let's move now to the interoperability module. The interoperability module is basically an out-of-the-shelf solution that developers can take, including their blockchain, and suddenly they have all the data structures, all the functionalities already available to have an interoperable blockchain. The storage interface of the interoperability module defines all the data structure that you need for interoperability. Here, I don't want to go through all the properties. I just want to look at the general store. The interoperability defines 3 different data structures: an interoperability account, when we store the properties of interoperable chains, for example, the inbox, outbox, but also the chain status and the set of validators, of current validators of the chain. The main chain will maintain an interoperability account for each connected sidechains, while the sidechains will only maintain an interoperability account for the main chain. We separated the outbox route from the rest of the properties of the interoperability account by defining a different storage prefix. These allow us basically to have shorter proofs of inclusion for the outbox route into the state route, because you don't have to pass all other properties of the interoperability account, you just need the outbox route. And finally, each chain will maintain an on-chain account, and in this on-chain account, which is created on a sidechain by the main chain registration transaction, we store the global chain ID of the chain in the ecosystem and the chain name. Of course, the interoperability module defines the transactions that developers need to run interoperability. In particular, we have 7 interoperability transactions. The first 2, the sidechain and main chain registration transactions, are used during the sidechain registration phase to connect the sidechain to the rest of the Lisk ecosystem. Then, once the sidechain has been connected, we go into the active phase where cross-chain messages can be exchanged between the sidechain and other chains in the ecosystem using the sidechain and main chain cross-chain update transactions. Finally, if for some reason, maybe an activity, maybe violation of the protocol, the sidechain is terminated. Users are still able to recover their tokens using the token and NFT recovery transactions, or pending messages to the sidechain outbox using the message recovery transaction, as Maxime explained in the previous presentation. The interoperability module exposes two reducers. Here, what we wanted was to streamline the creation and processing of cross-chain messages as much as possible. The idea basically is that other modules can call these two reducers to run the logic that they want to define around interoperability. In particular, the send reducer is used to create and send cross-chain messages. And as I mentioned, other modules can just call it from transaction apply to spawn a cross-chain message and append it to the outbox automatically. And the error reducer instead is used to bounce a cross-chain message. And this module in particular will allow for custom error handling by setting the status property of the message to whatever the custom logic needs. Let's look at the send reducer in particular. As I said, using this reducer makes emitting cross-chain messages extremely simple. Any transaction can emit one or multiple cross-chain messages. And the reducers creates the cross-chain messages from the input parameters. So what I show here highlighted are the properties that the transaction has to pass to the interoperability module to create the message, the module ID and the asset ID, the message fee, the receiving chain ID, and the asset where the custom logic is injected. All other properties like the index, sending chain ID, status, and the original index are automatically filled. And then the send reducer appends the cross-chain message to the outbox. The CCM then is included in a cross-chain update and routed via the main chain to the receiving chain. So here, the bottom line is that all the data structures that we need to interact with for interoperability, this interaction happens all behind the curtains. Really, the developer just needs to call the send reducers, pass these parameters, and then everything else happens automatically. The error reducer is used instead to bounce a cross-chain message in the case that the processing logic didn't work for some reason with an error code. So following the previous example, the main chain is trying now to forward the message to the receiving chain, is included in a CCU. But on the receiving chain, something happens. Maybe the asset schema was wrong, or there was some logic in the, error in the custom logic of the CCM. Then the custom logic can call the error reducer to set the status to a custom value. The sending chain and receiving chain are swapped, and the message is sent back again via the main chain. So here the idea is that there are some cluster errors related to interoperability that are automatically handled by the interoperability module. These errors are, for example, missing module ID or missing asset ID, or a chain, receiving chain that is not connected to the main chain. But there are other classes of errors, custom errors, that are instead handled using the error reducer. Okay, so this brings me to the last part of my talk. And here, again, we prepared this presentation to give you a pragmatic feel of how all these reducers and new modules interact to create custom logic, right? For this, we prepared this blockchain application that we call the Pirates of the 7 Chains. Pirates of the 7 Chains is a gaming blockchain application built on top of the non-fungible token module. We're going to define 3 things. The first one is going to be a custom gold token. This will be just the custom fungible token of our sidechain. Then we're going to define the custom properties that we're going to add to the NFT module. And finally, we will create a brand new Piracy Module. And this Piracy Module will define some custom transactions and the processing around cross-chain messages. But before diving in, what is the general idea? The general idea here is that we have our piracy chain that is part of the Lisk ecosystem, and we have pirates living in the piracy chains as NFTs. And these pirates are allowed to roam around the Lisk ecosystem. They're pirates, after all. And they can leave the piracy chain, get to another receiving chain, and then eventually come back to the piracy chain. And the custom logic is run whenever the pirate leaves the chain or returns to the chain. So our non-fungible pirates will be defined by these properties. As Maxime mentioned, an NFT is uniquely identified by 3 properties: the chain ID, which is the ID of the NFT chain defining the NFT, a collection, which basically corresponds to the type of NFTs, and an index. So to specify our pirates, we have to specify which collections are available. Then we have to specify the schema for the attributes property of the NFT. Each NFT has the properties that are indicated here: the owner, the locking module ID. We don't care about those for the moment, and the attributes. Here we store the properties that we need for the custom logic. And finally, we have to specify a function to update these properties when the NFTs returns to our piracy chain. Let's start with the easy one, collections. Here we just have to decide which type of pirates we want in our chain. We're going to have a collection 0 for the captain type of a non-fungible pirate. This captain will give bonus to Plunder. This will be a custom transaction that I'm going to explain later. Then we have a cartographer. The cartographer, again, there is some custom logic attached to it. It will increase the time frame of an adventure. More on this in a couple of slides. And finally, we have pirates. Collection ID 2. Pirates do nothing. They're just pirates. And we have a treasure NFT. This treasure, there is some custom logic attached to it. We can steal it during a Plunder transaction. Let's move on to the schemas. As I mentioned, we define the schema for the attributes property. Our pirates will have the following properties. They will have a level. This just indicates how strong the pirate is. They will have a visited chains, where we store each chain in the ecosystem, in particular the chain ID, where the pirate has been. And then we have this adventure object, which stores the chain ID, which is the target chain ID where the pirate is going, and the time frame, which is some sort of time limit before the pirate has to come back to the chain. And this adventure property is attached to one of our custom transactions. It will be processed as part of the custom logic. The treasure attributes, a treasure just has a single attribute, which is its value. It's an immutable property. There is no logic attached to it. It's just for flexing, nothing else. Finally, we have to define how the NFT attributes are updated. As Maxime mentioned, when the NFT comes back to the chain, we can run the custom logic on the NFT attributes. What we're going to do, we're going to check the adventure object. And if the adventure is successful, meaning that there is an adventure object to start with, the time frame, so the value that we were storing in the adventure time frame, is smaller than the current block timestamp, and the chain ID stored in the adventure has not been visited before, so it's not part of the visited chains, then the adventure was successful. The pirate has come back successfully from the receiving chain. We increased the level of the pirate became stronger. We create a treasure NFT as a prize. And to do this, we call the NFT create reducer to create the treasure collection for. And then we clear the adventure object in the non-fungible pirate attributes. OK, so now we can move to the Piracy Module. And this will be the centerpiece of our blockchain application. In our Piracy Module, we will now define the custom transactions and the handling and processing of the cross-chain messages. We will have 3 custom transactions. The first one, hire a pirate, very easy. You just use this transaction to create a non-fungible pirate. The second one, sale, will be used to send the pirate to any other sidechain in the ecosystem. And here I stress the word any, because really another sidechain may not implement the Piracy Module, most likely. But we are still able to send the pirate to that sidechain. And the sidechain will know nothing about what's happening. They will just receive the pirate. It's just an NFT for them. But then the pirate can come back, because can still be sent using the NFT module that is present on the receiving chain back to the piracy chain. And so basically, our idea is that this gaming blockchain works even if the rest of the ecosystem doesn't know that there is a game going on here. But finally, we have the last custom transaction, Plunder. This is used to steal treasures from other compatible sidechains, meaning that this transaction can be sent only targeting another sidechain that does implement the Piracy Module. or at least knows how to process the Plunder cross-chain message. Let's move to the first one, hire a pirate. Very simple idea. We have a set of hiring fees. This is the price for each pirate. The captain costs more, cartographer a little less, and then the pirate bottom of the barrel. This custom transaction defines an asset schema where we just have to put the collection, which is the rank of the pirate that we want to hire, so 0, 1, 2, or 3. We cannot hire a treasure. When the asset is validated, we check that the sender account has enough tokens to burn. This token, again, is the fungible token, is the gold fungible token of the sidechain. And when we apply the asset, we basically have to do nothing. We just have to call 2 reducers, already defined, implemented in the standard token modules. We burn an amount equal to the hiring fee using the token burn reducer, and we create the new NFT using the create reducer from the non-fungible token module. So far, so good. Let's now move to the second custom transaction, sale. Again, just to reiterate on the general idea, we have our pirate chain, and then we cast the sale transaction to set the adventure object of the pirate and send it to another sidechain. The pirates arrive to the sidechain. Then, after a while, the sender of the original transaction can send back the pirate to the piracy chain. It doesn't have to happen immediately. It happens in a later block. And once the pirate arrives back to the piracy chain, we update the attributes. If the adventure was successful, meaning that the chain has not been visited before and it didn't take too long for the pirate to come back, then we increase the level of the pirate. So this sale custom transaction defines an asset schema again, where we store the crew, which is an array on non-fungible pirates. So we can send many pirates at once to an adventure. And the receiving chain ID, which is the ID of the target chain, just the ID of the chain that we want to send our pirates to. To validate the asset, we check that all pirates are actually in the sender account. And when we apply the asset, what we do, we create the adventure in the attributes property of the non-fungible pirate by calling the NFT reducer set attributes. If we have a cartographer in the crew, this is what I mentioned before, then we give a time frame bonus to each adventure object. Finally, this cross-chain transaction emits one cross-chain message for each pirate in the crew. And to do so, it calls the NFT cross-chain transfer reducer to send the pirate to the target chain. So the corresponding message that is spawned automatically by the NFT reducer as an asset that looks like this, where we specify the NFT ID, the sender address, recipient address, and attributes. But this is all done automatically for us by the NFT cross-chain transfer reducer. And then again, once the pirate arrived in the receiving chain, then the sender can send them back to the piracy chain, and the adventure is processed, and eventually the attributes updated. And our pirates get stronger, which is very important, because the next custom transaction, Plunder, allow us to attack a user in another compatible sidechain. The general idea here is that we start from the piracy chain, we take our crew of pirates, and we send them on a receiving chain to attack a user. Here, a battle happens. This battle is just some custom logic that we run in the receiving chain, because the receiving chain also implements the Piracy modules. And automatically, after the battle has been resolved, the pirates are sent back to the piracy chain, no matter the outcome of the battle. And then the pirates arrive back to the piracy chain. As I mentioned, we use Plunder then to attack a user in another compatible sidechain. The asset schema of this transaction is very similar to sale. We have a crew, which is the array of non-fungible pirates, and the receiving chain ID, which is the ID of the target chain. But now we also have to specify the target address, which is the address of the user that we want to attack. To validate the asset, again, we just check that all pirates are actually stored in the sender account. And to apply the asset, this time what we do, we first cross-chain transfer all the pirates in the crew, the same as what we did for sale. We don't set the adventure in this time. This is not a game. We're attacking someone. All these non-fungible pirates are then sent to the receiving chain, and after these cross-chain messages have been appended to the outbox, after this, we call the interoperability send reducer to create a Plunder cross-chain message. This is our custom cross-chain message that stores the sender address, the target address, and the crew. And this will be used to run the custom logic on the receiving chain. So how do we process these cross-chain messages? We compare the strength of the attacking and defending crew. To do so, we just sum the level of each member of the crew, and we add a bonus for the captain. If the attacker wins, the attacker steals a NFT, a treasure NFT from the defender. And to steal it, we just, again, call the NFT cross-chain transfer reducer. If the defender wins, on the other hand, a member of the attacking crew is transferred to the defending player using just the NFT transfer to the defender account. This is an internal transfer because they're both already on the receiving chain. And then, no matter what happens, we send back the crew to the native chain. Just, again, an NFT cross-chain transfer of the crew back to the sending chain. But what happens if, for some reason, as I mentioned before, first the pirates are sent to the receiving chain, and then we have the Plunder cross-chain message that triggers the custom logic that I explained in the previous slide. What happens is if for some reasons the pirates are not in the sender account anymore. Maybe the messages have been split into different cross-chain updates. In this case, we cast an error on the custom logic. So again, we check that the crew is indeed in the sender account on the receiving chain. If this is not the case, we set the status to the error code, missing pirate, using the interoperability error reducer, and we send whatever is remaining of the attacking crew back to the native chain, again, using the cross-chain transfer. And then on the original sending chain, our piracy chain, we can trigger some custom logic if we want. Maybe we can punish the attacker because they cowardly ran out before the battle. OK, this brings me to my last slide, where I want to summarize what I talked about. I presented the novelties that are coming in the updated version of the SDK, the one bringing interoperability in. These novelties will take place after the interoperability leaps have been implemented. In particular, we will have a new state model, and we will have also all the logic that is around the cross-chain messages processing. In particular, the interoperability module is an out-of-the-box solution that developers can use. They can register the interoperability module to their blockchain application, and suddenly they have in place everything they need to start interact with the Lisk ecosystem. Finally, I presented an example of an interoperable blockchain application, the Pirates of the 7 Chains. Here we tried to put together what we discussed before, and we saw that using the interaction between the NFT modules that we customize and the new module that we created, you can create some non-trivial logic that allows for this gaming example. The bottom line here is that interoperability is coming. So now is the time to get your hands dirty and start projecting an interoperable blockchain application. With this, I thank you.